Yes, thank you. Thank you very much, Anatoly, for a really nice talk. So I haven't seen any questions in the chat yet, but if people can raise their hands, if they want to ask something. Maybe I can start with one first question. You had this example in the beginning, right, with XIS of the different sites on this particle. So, I mean, I guess one problem is with this that, you know, if, as you mentioned, if the particle is too big, only a few of the sites really are the active ones, right? And it's, the signal is really swamped out by the other ones. So I guess when you have these very small dilute materials, then it's easier to do, but for the bigger ones, this is generally a problem because it's out of the spectrum. Only very small contribution is really the relevant one. Is this correct?
What do you mean by bigger materials?
No, I mean, if you have a large material, right? If you have like only like very small ensembles, like 2 or 3 atoms, then I think it's easier to figure out what's going on. But if you have a lot of nanoclusters, then there's very few corners and edges, right? So
right.
most of the spectra is really not useful, right?
Yes.
So how do you...
Yes. So we cannot do what cannot be done. So we really that's why I focus my research on those materials in which there are questions in the local structure. If there is if the material is useful because of its bulk properties, it's of course very interesting class of materials for functionality, but we cannot contribute so much to, at least I don't have much contribution to that. So I'm looking for materials in which there is some unsolved question. For example, nanoparticles, as you correctly said, when you increase the size beyond, let's say 3, 4, 5 nanometers, they will have bulk atoms dominating the spectra, and you can't use this method for that, or maybe not yet, because in principle this method is not limited to decoding X-ray spectrum. For example, if you measure IR spectrum, that still, or XPS spectrum, that still has some relationship to some descriptor, you know, of structure or vibrational mode of some sort. It's still philosophically the same idea. Like if you have a way to train a neural network to recognize this relationship, you probably can also invert that as well. But going to your question, yeah, this is a limit. That's why alloys are very useful, because in alloys, even if they're bulk, there's some interesting questions in the local structure, because the compositional motifs, even in the bulk, may range from homogeneous to heterogeneous. They range from positive short-range order or negative short-range order. And these are very difficult to detect, especially in operando conditions. And XR's coordination numbers are key for measuring, for example, whether it's positive short-range order or negative short-range order. And we can actually train neural network to do that, and it doesn't require this site-specific training. We have a different approach, which I didn't discuss. But yeah, what I show on this slide is actually we tried to go with the size increase from just a dimer, and we see very strong change in the Zanes. You see the distance is the only parameter that changes in the dimer. There's nothing else to change. And you see that Zanes changes like dramatically. So if you have a question about, you know, diatomic gas, you can answer it very easily using XR. But it's just an exercise.
Thank you. Yeah, so students first. Florian, you have a question.
Yes, so you said in order to have a bigger data set, you look at the single atom of a nanoparticle, right? Or am I mistaken?
Yeah.
Okay.
So let me show you the cartoon for that. Here you go.
Yes, so yeah. I'm not educated on a single atom catalysis, but isn't there an issue with disorder effects when you look at single atoms with XRs? So how do you guarantee that your data set is actually getting better by looking at a single atom?
No, I'm going to show to you the very quickly a different document. I'll just walk you through about the manuscript it's currently in review, but it's okay. Which solved the problem of single atom cutting.
Okay.
This method. Just give me 1 second. I need to open it on my screen first. Just a second. Well, anyway, I'll start talking while I'm looking for it. So in order to account for disorder, we need to account for different modifications, different transformations of the local structure. So our training involves, first, we need to identify which descriptors we want to focus on. So we can't find, and we learn it from our kind of trial and error. We can't find all the surrounding atoms of the single atoms, because then it becomes very degenerate. I mean, the problem becomes very degenerate. So we really had to focus on just few important descriptors. And let me find that paper quick. Yeah, sorry for spending so much time on that, and I need to also learn how to make it bigger. Here it is. So this is the system we analyzed. So this is cobalt single atom grafted on C3 and 4 support for photocatalysis, CO2 photoreduction. And you see in the center, it's the catalytic species that may change their coordination during the reaction by replacing the top ligand by hydroxyl, carbon monoxide, and carbonate, CO3. And so the question was, how do we recognize this change in the structure? Because we could very easily follow reaction pathway, we could see formation of the products, and we wanted to correlate it with the structural changes, but it's a single atom system. So what we did first is we followed the reaction sequence, not the reaction sequence. We followed the reaction in real time using X-ray spectra, and we obtained the sequence of spectra in which they were continuously changing. Trying to find that figure. Oh, this is not really a good example. Here it is. It's not in the right order, but at least the figure will show up hopefully somewhere. It just did. So here you go. So the left figure shows how the spectra transform from t equals 0 to t equals 143 minutes. You see that figure, right?
Yeah.
And so this is a single atom, but it has so many spectra. What to do about that? And so we did what any person would do dealing with spectral changes, would apply, singular value decomposition. How many spectra are there mixed together? Because we know that in reaction kinetics, you have starting phase, intermediates, and the products, right? So we found that there are exactly 3 structures. Then we used a spectral analysis, completely objective, without any assumptions, any neural network, to generate pure spectra from this mixture. Pure spectra of some unknown structure, but it was at least not mixed with others, and that's why we can start analyzing it. And so that's the second necessary step. And if you can do it with principal component analysis, you're lucky. And in this case, we were lucky. But in those cases with nanomaterials, you can't usually, because principal component analysis requires some kind of standard that you rotate your basis of components to match the standard. But you don't have standards in the nanomaterial world. They are all non-bulk like. So, and you cannot use theoretical standards. So here we're lucky, but in principle, there is a method called MCR-LS. And that method allows you to objectively, without any prior knowledge, or with minimum prior knowledge, to get the spectrum. So we ended up having the spectrum. You see that there are eigenvalues showing that we were successfully deconvoluting this into just 2 or 3 most important spectra. And then we obtained the spectrum of the structure that we wanted to analyze. And this was the structure shown here by C. That's the one on the right. And then we had a sensitivity test. So our theory included different parameters: the distance to carbon and the distance to oxygen. And we could not vary anything else because this cyclone structure is very well known and it's fixed. There's no reason to vary anything. It's not, no disorder is allowed there. So only vertical bonds. We tried to vary the angles, but it was not successful. And so you see that even with this sensitivity test, you can see that there are some structures that fit experimental data without even doing any machine learning. Machine learning simply, they did it quantitatively. So here is an example on the left. We have this absorption coefficient, the input layer, and the output layer has just 2 descriptors, DC and DO. So that's the type of disorder the question was about. And that's how we handled it. We generated many, many training sets shown by these curves to be very unique and having a lot of contrast. And that's why it worked. Sorry for the long answer to a short question.
Okay. No, that was very nice. Thank you. Günther, you have a question.
Thanks. Yeah, hi. Thanks for the nice talk. Well, I'm not sure if it's a question, it's maybe it's a half question, half a comment, because you mentioned yourself infrared. So, for instance, for the palladium gold system, and I was just noticed that, I mean, a while ago we looked into single palladium or few palladium atoms in gold clusters and used infrared with CO to probe the surface. But then, of course, with this, you always have the problem that the CO also pulls out the palladium to the surface. And so, of course, like what you showed, if you want to see the difference in pure hydrogen or in vacuum or in pure oxygen, of course, then you cannot really use the CO to probe that, right?
To a degree,
Yeah.
For exactly the same reason you explained, we went to the low temperature regime where the CO cannot drag thermally. Because palladium cannot be easily thermally.
Yeah, sure. Yeah.
So at Brookhaven, at CFN, at Center for Functional Nanomaterials, they have a low temperature IR setup, transmission IR setup that we collected nice data, actually confirming these ensembles and decoupled that from thermal, from CO dragging them to the surface.
And that was liquid nitrogen or what?
That was liquid nitrogen, right?
Yeah. Okay.
Yes.
Yeah, it's a good idea. Yeah. Thanks.
Okay. Are there any more questions? Michael? Michael, you have to turn on your microphone. We cannot hear you.
It's very interesting for me because we did that system many years ago with STM just in UHV, the palladium, silver, and also palladium gold alloys. And one thing that comes into my mind, if you see trimers of palladium, then it will not happen according to our STM study. So it can only happen if it's bound to oxygen. So if the three palladiums are bound to oxygen, of course this probably would strongly affect the xenes in a way that is quite different from what coordination would do. So can you comment on this? Do you think you have oxygen there, and it will affect the it would also affect, of course, the reactivity?
Thank you for this question. It's a question that is a recurrent question in our team because theorists, especially Philippe Sauté and others, picked on that oxygen should have been detected by Zanes if it was there. And we specifically looked for the effect of oxygen on Zanes. And without Zanes, we wouldn't be able to use any other method to detect it, and we couldn't see it. So I do not know if the reason is that maybe oxygen bonding was weak, and if it is weak, maybe the perturbation of the electronic structure of palladium was weak because Zanes doesn't see really bond like EXAFs. So it sees some changes in the, in the density of states and the transition region, but we just didn't see it. So I have no, and I agree with you that it was expected because I hear that sentiment, from many people. I was just, we couldn't observe it. I don't know why. Maybe gold pulls oxygen on it, or maybe there's some other explanation, but we just couldn't see oxygen.
Okay. And it's sensitive enough to see the oxygen?
Sorry?
It would be sensitive enough to see the oxygen?
We don't have anything to compare with because it is in principle, of course, if you have palladium nanoparticle, we could see oxygen very nicely if it's oxidized. Have palladium oxides, we see obviously oxygen, and it has its own signature. But we did not have such a control of palladium dimers with oxygen to detect it in this experiment. So it is not easy to say if it is detectable if nobody has ever done that. You don't have anything to compare with, basically.
Yeah, I mean, say if you have the oxide, you can guess how many oxygens you have there, and then compare how big is the signal, and then compare, say, assume for each palladium dimer at the surface you have an oxygen. Could I still see this by just scaling?
Let me show to you just temporarily the same presentation, but with EXAFs, that you will see where oxygen would have been, because EXAFs is more direct, right? So this is the data, and if oxygen, you see where my cursor is. So if oxygen were to be found, it would be somewhere in this range. And it is maybe or maybe not consistent with the fact that under oxygen conditions or right after oxidation, the signal is a little bit higher than after hydrogen reduction. But fitting it with oxygen is very speculative, and we couldn't find anything from that. So, if you get something from the fit that gives you a good fit, but with a huge error bar, it's really not informative for any purpose. I would just be more conservative and say we can't tell it, rather than to say it's not there. I think we just don't have enough confidence that we can detect it. On the other hand, one can ask, what if the changes in the zenes are convoluted? And there is also some effect of oxygen that affects the zenes, and we don't know about that. And to that, I can say that machine learning actually has a good eye, because it can detect, and this is why it's so beautiful, because it doesn't require all the correct variables to be included in the model, only the partial ones. For example, in the fit, you cannot get a good fit unless you properly account for all data behavior. But if you have a partial set of variables, but not all, you can still find them. And this is, of course, not a general scientific statement. It's just like from experience. From the neural network, you can find the parameters while you don't find all of them. But those which you find are still reliable in those limited experiments that we tried. So by not including oxygen, we probably are not compromising the results for dimers and monomers. That's the main point.
Okay. Well, thank you very much, Anatoly, for the exhaustive answers, and thank you for the questions.
Thank you.
I want to close the colloquium now, but I want to, ask people who have an appointment with Anatoly now, which is our own sub-project. So, invite